So remember, I was trying to prove this lemma. So again, the situation is this: we have the positive solution of the heat equation. M is complete, n-dimensional, complete, boundaryless, and I'm assuming that G bigger than or equal than 0. And we take f to be the logarithm of u, and then we define capital F to be t times gradient f squared minus alpha ft. Alpha is any number bigger than or equal to 1 at this moment. So lemma Laplacian f minus ft is bigger than or equal than minus 2 gradient f gradient capital F. This is the Riemannian inner product. Okay, I will denote it like that for simplicity. Plus 2 over n times gradient f squared minus ft squared minus gradient f squared minus alpha ft. Notice that the last term is capital F over t. Okay? So this is a pointwise inequality. And as I said last time, this inequality is just based on some calculations and Bochner's identity. But it will prove very useful in the proof of the theorem of the ADR. Okay? So the purpose of this lemma is to estimate from below, as you will see in the proof of the Liao inequality, this term here. Because you can bring this object to the right-hand side, and you will see that at a point of maximum, this object is bigger than or equal than 0, so you can throw it away. And so essentially this lemma tells you that this is bigger than or equal than that. Okay? So, so remember that this just follows from Bochner. So let me give you the proof of this lemma. You know, it's as I said, it's just a calculation. So let me start with the Laplacian of this function. So I have Laplacian of f. It's going to be the Laplacian of this guy, which is 0, times this times the Laplacian. So it's equal to t times the Laplacian of minus alpha ft plus twice. And then there is the gradient of this inner product with the gradient of this. The gradient of this is 0, so we can get rid of this guy here. So that's all that there is at this moment for the Laplacian of f. So this is equal to t times. So here now I'm going to use Bochner's identity. So let me recall Bochner's identity here. Okay, so as you see, the identity is good for us because we're going to want to calculate this object here. So let me substitute what we get from the identity then. So here we get plus twice gradient f gradient Laplacian f plus plus twice Ricci of gradient f gradient f. Okay, so this is t times this. And then we have minus alpha t times the Laplacian of ft. Okay, so now I use Newton's inequality. this is the Hilbert-Schmidt norm of the Hessian, the square of the Hilbert-Schmidt norm of the Hessian of f. The Laplacian of f is the trace of the Hessian. So Laplacian of f squared is less than or equal than n times this. This is just Cauchy-Schwarz inequality if you wish, but it's called the Newton's inequality for matrices. The fact that the square of the trace of a matrix is less than or equal than the dimension times the Hilbert-Schmidt norm of the matrix. It's just Cauchy-Schwarz inequality. Cauchy-Schwarz Boniakowski, since I'm here. I was taught when I was a young guy that this is called, the Cauchy-Schwarz is called Cauchy-Schwarz Boniakowski inequality. So, and anyhow, so we get this thing here. So let's estimate from below this guy. So we get Laplacian of f bigger than or equal than 2t over n times, times this. And then we have plus 2t gradient f, gradient Laplacian f. I will leave it like that for the moment. Plus, remember, t for us is bigger than 0. We are looking at m cross 0 infinity. So I'm assuming that reach is bigger than or equal than 0. So I can just throw this away because I'm estimating from below. This object here is bigger than or equal than 0 because of this assumption. So I can throw this term away. And then I'm left with, so since I'm putting bigger than or equal, I have minus alpha t Laplacian of ft. Okay? So that's what we get. Now let's look at ft. Ft is going to be equal. So one time I put the derivative here, so we get gradient f squared minus alpha ft plus, and then we get t times twice gradient f ft minus alpha ft. Okay, so now we have both ingredients that we need to estimate from below. So now we get the heat of f is bigger than or equal than 2t over n Laplacian f squared plus 2t gradient f gradient Laplacian f minus alpha t this, and then we have minus gradient f squared plus alpha ft minus, let me write it to the next slide, minus t times twice gradient ft minus alpha ft. Okay, so that's what we get. So let me see. What can we do now? Okay. So let's remember now the equation satisfied by f that I told you yesterday. You know, since f is the logarithm of u and u is a solution, remember yesterday we observed that the equation satisfied by f is the following one. I computed on Saturday this equation here. So I'm going to apply this equation to, I'm going to use this equation now many times. So let's see. So let me call this star. So by star, we can continue here, and we get equal to 2t over n times Laplacian f squared. Remember that Laplacian f is equal to, according to this equation, is equal to ft minus the length of the gradient of f squared. So I'm going to replace it in here. Then I get minus 2t gradient f gradient of this object here. So I'm using this equation here. Then I get minus and minus, I get plus alpha t ft. So let me put, then I get minus alpha t Laplacian of ft coming from here. So this guy here is here, this is here. And then we get minus gradient f squared plus alpha ft. And I think I have everything at this. No, there is one piece missing, and it's this one. So no, that one gets cancelled by the other term here, because Laplacian f is ft minus this. So I get 2t gradient ft, that cancels this one, minus 2t gradient ft. Is it clear what you see? In this term here, this term gets replaced, this term here gets replaced by the Laplacian of f is replaced by ft minus this. So one time I get 2t gradient ft coming from here, and that cancels this one. I have minus 2t gradient ft. So this is all. Okay? Is everything clear? I mean, if there is any doubts, please stop me, because this is just calculation, so we need to understand what's going on. All right, so on the other hand, since we have f given by this expression here, then this also gives us that t gradient f squared is equal to, so t gradient f squared is equal to capital F plus alpha t ft. Okay? And I'm going to use that information now in here. Okay, so so according to this observation here, we get minus 2t gradient f gradient of this. So this is equal to minus 2t gradient f. Then I get, so t goes inside because it does not depend on the gradient, so I can put it here, and then I get the gradient of capital F without the t. Okay, the t goes inside, and then I use this formula. So I get this, and then I get plus, so I have minus 2 alpha t gradient ft. Okay? Right. So in the end, what I get is that this is bigger, so this is, if you wish, equal to 2t over n. I'm going to replace the Laplacian of f again. The Laplacian of f, where is the equation? It's right here. Laplacian of f is ft minus this, so I can replace this guy here with gradient f squared minus ft squared. So this goes to this using this equation. And then we get minus 2 gradient f, gradient capital F, using that identity there for this. And then we get minus 2 alpha t, gradient f, gradient ft, plus alpha t, ftt, minus alpha t Laplacian of ft, minus gradient f squared plus alpha ft. So this is what we got, that this thing here is bigger than or equal than this. Okay, so now I need to understand this term ftt. And again, I'm going to be using this equation over and over. So let me delete this and this. So ftt is equal, according to this equation, to Laplacian f minus this. So Laplacian f, plus this e. And this gives, yes?
Equal.
Oh, sorry, equal. Thank you. And this gives Laplacian ft. I'm trying to understand the Laplacian of ft. So Laplacian of ft plus twice gradient f, gradient ft. So if we substitute this expression into this inequality here now, I'm going to use it for getting that one, we obtain I guess that this, I will not need it anymore. So what we get is Laplacian f minus ft bigger than or equal than 2t over n. So we have already gradient f squared minus ft squared minus 2 gradient f, gradient capital F. Then we have minus 2 alpha t gradient f, gradient ft. Then I have plus alpha t ftt. And instead of ftt, I'm going to use this thing here. So I have alpha t which multiplies, so plus alpha t which multiplies Laplacian of ft plus 2 alpha t which multiplies gradient f, gradient ft. And that takes care of this guy. Then we have minus alpha t Laplacian of ft. That's good because we will cancel that guy. And then we have minus gradient f squared. We are almost finished. Minus or plus alpha ft. So this and this cancel. This and this cancel. And let's see what we wanted to prove. So we have this guy here, we have this guy here, and then we have this guy here. We're finished with this calculation. Okay? It looks like a magic calculation, but of course, you know, they knew what they were doing, because now we have to see how this is used. So, remember, in this lemma, which I just proved, all that there is Bochner's identity, and then clever calculations. Okay? Any questions? We're finished with this one, so let's move on now to the proof of the main theorem. All right, so before I prove the main theorem, I must say that yesterday I managed to prepare Russian style my first Pernieni, and I succeeded. It was thanks to the help of Nastia, who told me what to do, but I managed. So it was delicious. The problem is that I ate the whole package, so today I have lots of curvature. I'm not richly flat. Okay, so now let's go back to the main theorem. So let me recall it for you, since it's no longer on the blackboard. So remember the assumption, so the main theorem is assumptions as before, assumptions on M as before, so I will not repeat them. Remember, I'm assuming in particular that Ricci is bigger than or equal than 0. And then U is assumptions on M and U. U is a positive solution of the heat equation. And then we want to show that there exists a universal constant Cn bigger than 0, such that for any r bigger than 0, actually this theorem is a local theorem, because I don't even need to assume that U is a positive solution in the whole manifold. It's enough to assume that U is a positive solution in a geodesic ball of radius 2r, and then we get the estimate in a ball of radius r. So this is really a local theorem. So for any r bigger than 0 and for any alpha bigger than 1, the supremum of over dr, so geodesic ball of radius r centered at some point capital O, of gradient u squared over u squared minus alpha ut over u is controlled by this constant times alpha to the 4 divided alpha squared minus 1 r squared plus m alpha squared over 2t. So this was the main estimate of Li and Yao. And as I showed you on Saturday, from this estimate, first letting r go to infinity, and then alpha go to 1, we get the final estimate of Li and Yao, which is this one. Where f is the logarithm of u. So you see here, this is the length of the gradient f squared. This is ft. So alpha goes to 1. So we get this quantity here. This goes to 0 because r is going to infinity. And this goes to n over 2t. Okay, so that this is the Liao inequality in the case of Ricci bigger than or equal to 0, and it follows immediately from this theorem. As we already went through this proof here. So, okay, so this is the estimate that we want to prove. And well, the first thing that we need to observe is that we can convert this statement into a statement for function capital F that now is disappeared from the blackboard. But let me write it again here. So remember, in this lemma here, capital F is E gradient F squared minus alpha Fe. So you see that where F is the logarithm of U, F is the logarithm of U. So I could rewrite this as this, supremum of capital F over T in BR. Remember here T is fixed. T is a time which is fixed, and I'm taking the supremum in a geodesic ball centered at the point capital O with radius R. So this is less than or equal than Cn times alpha to the 4 divided by alpha squared minus 1 R squared plus n alpha squared 2t. So essentially what we need to do is to estimate the supremum of this function capital F. So this is, in order to prove the theorem, we need to prove this thing here. Let me call it double star. Okay, and the idea is to apply the maximum principle. Very classical and simple idea. But as you will see, it really takes an ingenious new trick to implement this idea. And this is a remarkable idea of Li and Yao. Okay? So we want to apply the maximum principle. So let me draw a picture here. So let me suppose that this is BR, this is B2R, and I'm going to start making some preliminary considerations. So let psi be just a function on the line, so which I'm going to be choosing suitably. But this is the proof of Li and Yao. I'm not telling you anything new, okay? So, 0 less than or equal than psi less than or equal to 1. Let's take psi to be identical equal to 1 on 0, 1, and psi 0. So let me draw a picture here. So this is our psi. And psi 0 outside 0, 2. Okay, so with and let's also assume so psi is going to be decreasing. So psi prime is less than or equal to 0. Let's suppose that the curvature of psi is under control. So psi double prime is bigger than or equal than minus C1. C1 is some absolute constant. And then I'm also going to assume, which can be done, you can see by yourself, that you can choose psi in such a way that psi prime squared divided by psi is controlled from above by another absolute constant. Okay? And now we let phi of x to be psi of rho of x divided by r, where rho of x is the geodesic distance of x to this center of the ball. So I take essentially a function which depends only on the distance, so some kind of radial function. Although this distance is just a geodesic distance, and we know that this distance is Lipschitz on the whole manifold, but it ceases to be smooth when we hit the locus of capital O. So we have a problem there. And you know, I want to apply the maximum principle, so I want to apply the tools of calculus. I want to take first and second derivatives, so I have to be careful. Okay? I have to be careful. So the first thing, okay, so let's erase this stuff here. We don't need this stuff anymore. Ooh. Oh, the lemma is here. I only need this stuff. So, well, as you will see, I do not only need this lemma. Now the game becomes really a little bit more involved, because we will need, besides this lemma, which involves only Bochner's identity, we also need the Laplacian comparison theorem at some point. So, I might have erased an equation which I will need to use again, but we'll see. Okay. So let's consider the function phi times capital F. So phi is just a cutoff function constructed like this. So this function is 1 in the ball of radius r, and it's 0 outside of the ball of radius 2r, because of the properties of psi. Okay, so let's suppose that phi times capital F attains its maximum at a point x0 t0 in the ball of radius 2r Cartesian with 0 capital T, where capital T is some number fixed. Okay? First observation, I want to prove this inequality here. If the supremum, if that maximum or supremum, how you want to call it, is negative, then there is nothing to prove. Because the supremum over here is less than or equal than the supremum on the bigger ball. If it is negative, this quantity is positive, so this becomes a trivially true. So we can assume that f at x0 t0 is strictly positive. Because if f was negative, as I said before, the inequality otherwise double star is trivially true. Okay? We can also assume that T0 is strictly positive. Why? Because if T0 is equal to 0, remember the definition of f, which I'm sorry, you know, f disappears from the blackboard, so I will rewrite it again. F is this function here. So if T0 were 0, then f would be 0 at x0 t0 against this assumption. Okay? So I can also assume this without loss of generality. Any questions? Okay. So then we have x0 in B2R, and then we have 0 less than T0 less than or equal than capital T, at which this maximum or supremum is attained. All right, so we have two possibilities. We distinguish two possibilities. Possibility number one, x0 does not belong to the cut locus of O. Remember, all these balls are centered at a point capital O in M. So there is this point x0 here. So the cases are two. Either x0 is not in the cut locus of O, and therefore function rho is differentiable at x0 by definition, or x0 is in the cut locus of O, and then we have to argue differently, because we cannot differentiate, apparently. Okay, so I will discuss mainly the case, this is the difficult case. This case can be handled by a simple trick, which in Riemannian geometry is called the method of support functions. So one moves up the point a little bit and you know, arranges things in a suitable way, but I'll tell you what the idea is at the end of the thing. But the difficult case is case number one. So case number two is x0 belongs to the cut locus of O. In this case, we essentially reduce the discussion to case number one by the method of support functions. And that's a standard method in Riemannian geometry. All right, so let's look at case number one then. Now I'm going to focus on case number one. All right, so as I said, I'm outside of the cut locus of O. Then function rho is differentiable, is C infinity in a neighborhood of any point, in a neighborhood of x0. And therefore phi is C infinity, so I can differentiate. So I'm assuming there is a maximum, so the standard calculus tells me that 0 is equal to the gradient of phi times f. These calculations now, they all take place at x0, t0. Okay, so whatever I'm going to say now, so I don't write the argument for simplicity, otherwise it becomes too long, but think that everything I'm going to write here is done at x0, t0. So at a maximum point, I have gradient 0, so that tells me that this plus this is 0. So in particular, the gradient of f is equal to minus f gradient phi over phi. Okay? At the maximum point. So second assumption, we have 0 less than or equal than phi f t. Remember, it's a maximum point. It's not attained here, so it is attained either here or here, so the derivative is positive. Okay? And that, since phi does not depend on t, this is the same as this. And since phi is function bigger than or equal than 0, ft must be bigger than or equal than 0 in particular. So condition number 3 is that it's a maximum point, so Laplacian must be less than or equal than 0. So third thing, 0, Laplacian of phi f is less than or equal than 0. And so you will see now how from this thing here, Li and Yao, with this remarkable argument, they deduce this inequality here. So this inequality will come from this third condition. Okay? All right, so let's see. I'm stuck because I put this inequality right in the middle of the blackboard. So I'm sorry, I have to go around it, but it's what it is. So let me keep it because I will need it at some point. All right, so now let me rewrite this. So I have 0 bigger than or equal than Laplacian of phi f. So this is equal to phi Laplacian f plus f Laplacian phi plus twice gradient phi gradient f. And now you see where the things start coming into the play, because I have an inequality that goes into this direction. So I have to estimate Laplacian capital F from below. Look at what this lemma is telling us. And I have to estimate the Laplacian of phi from below, because I have to continue this inequality until I get something interesting. Okay? So this is done by this lemma. This one, as you will see, will be done by the Laplacian comparison theorem. This term is innocent because this term is, you see here, that equation tells me all my calculations are at x0, t0, remember. Okay? So I take derivatives, but then I compute them at x0, t0. All right, so let me replace, first of all, this there, using this fact here, by minus 2 capital F gradient phi squared over phi. Okay? So now, remember my assumption. I'm away from the cut locus of O. So I can differentiate the distance function. And therefore, what I get is the following. So I get the Laplacian of phi now is equal. So remember, phi is composition of two functions. Is this composed with this? So if I take the Laplacian, I'm going to get 1 over r squared. So I get 1 over r squared psi double prime evaluated at rho over r times the gradient of rho squared plus 1 over r psi prime rho over r times the Laplacian of rho. That's calculus, chain rule. Okay. So let me get rid of some stuff here. And let me see. So we were down at this point. Okay. So here, if we use, we can continue and say that this is, remember the Laplacian comparison theorem. Let me see, where can I erase? Maybe I can erase up there. We will not need this anymore because this is what we need to prove. So I can get some space. So this is where I'm going to be using, in a crucial way, the Laplacian comparison theorem that says this is less than or equal n minus 1 over rho. Remember, yesterday I showed you that if reach is bigger than or equal than 0, then the geodesic distance satisfies outside of the cut locus this inequality. Since I'm assuming that x0 is outside of the cut locus, then I have this. But remember that I'm taking psi decreasing, so psi prime is less than or equal to 0. So if I multiply by psi prime here, I reverse that inequality. So I reverse that inequality, and so what I get is that the Laplacian of phi at x0 is bigger than or equal than 1 over r squared psi double prime rho over r times gradient of rho squared minus n minus 1 over rho, 1 over r, psi prime, and here I can put this, because, you know, minus the absolute value of psi prime is just psi prime. So, here I've used crucially this ingredient. Please do not underestimate the importance of this step. When you switch from Riemannian to sub-Riemannian geometry, this is the beast. This is the bad moment. Because in sub-Riemannian geometry, there is no general results of this kind. There are some special cases which have recently worked out by Andrea Grashov and Paul Lee, but only for three-dimensional manifolds, and the general theory is still missing. I mean, that's the beast today. And, you know, I suspect, and I talked to Andrei many times about this, that the general theory of this object here in sub-Riemannian geometry is never going to come, because you don't have a rich supply of Jacobi fields to say in every sub-Riemannian manifold this inequality here. But anyhow, so there is a lot of work being done. Andrei, of course, so Andrea Grachov is Paul Lee, Igor Zilenkio. They are all working, you know, on trying to, well, Zilenkio is working on developing a theory of Jacobi fields. So anyhow, so there is this moment in which, you know, this happens. And it's the crucial moment in Riemannian geometry. So now let's remember that the support of function psi is, you know, so psi, you know, we have, so r and 2r here for psi of rho over r. Okay, so this is the support of this function here. So we are away from 0, and therefore here we can just use simple considerations to say that
support for psi to prime.
Hmm?
You have drawn the support of not psi but psi to prime.
Psi prime.
Psi prime.
Yeah. So this is the thing that I'm working with. So so here we can simply say now at this point that the Laplacian of phi is bigger than or equal than minus n minus 1 over r squared times absolute value of psi prime rho over r, and then we have minus c1 over r squared here. Remember that rho satisfies the aconal equation, so this is always equal to 1. And so therefore you can remove this thing and use assumptions, this assumption here on psi double prime to get this estimate here. So this follows, this one follows immediately from this one. And the fact that I can replace rho with r here comes from the fact that the support of this function is between r and 2r. Okay? So now we get this thing. So at this point, so we finally obtain, let me write it over, let me write it, I'm still stuck, I cannot erase this thing here, so let me write it here. Okay, so the conclusion that we get is the following, that 0 is bigger than or equal. Remember, we have 0 bigger than or equal than this. Now I've used the Laplacian comparison theorem to estimate this guy from below. The inequality is preserved because f at x0 t0 is assumed to be positive. So I'm not destroying the inequalities when I multiply this by f. And so what I end up with is the following. So I get, I will just give you the final product, I mean, without dwelling too much. So phi times Laplacian f, and here I have minus capital F, which multiplies n minus 1 times absolute value of psi prime rho over r plus C1 plus 2C2, everything divided by r squared. Okay, so this comes from here. Okay. So where does this one come from? This one comes from estimating this guy. You see, the gradient, I mean, I won't give you all the details because they are very boring, and Nastia is going to fall asleep. So the gradient of phi is, once again, is 1 over r psi prime rho over r times the gradient of rho. So when you put this thing squared, you get this squared, squared. Now psi prime squared, you see, is controlled by C2 times psi. So when you plug everything in here, then you get this term 2C2 in this. So this is where this is coming from. This is coming from this piece here. Okay, so that's what we get. So at this point, we have used the Laplacian comparison theorem to estimate the cutoff function, the Laplacian of the cutoff function. Now we need to use this lemma to estimate this guy from below. Okay. So, all right, so let me make the observation then. It's written here. Look at this inequality here. Ft is bigger than or equal than 0. Phi is a non-negative function. So Ft at x0 t0 is bigger than or equal than 0. That means that in this inequality, when I bring this guy to the right-hand side and I calculate everything at x0 t0, I can throw it away. So I can throw this guy away in this inequality. And then this inequality tells me that the Laplacian of f at x0 t0 is controlled from below by this quantity here. Okay, so now I'm going to insert this information in there. So, allow me to erase this because at this point I won't need this anymore. But I will keep this in the box because I will need it one more time. So what I get now is that phi times Laplacian f is bigger than or equal. Then phi, well, I already said I'm going to kill this guy, so I get minus 2 phi gradient f, gradient capital F, plus 2t over n times phi times gradient squared by minus ft squared minus gradient f squared minus alpha ft times phi. Okay, so this is what we get from the lemma. Now finally I can erase the lemma. Okay, So let me erase the lemma. I've used it to control from below this object. So finally now we have some space on the blackboard. Okay, so now, so let me introduce for simplicity a notation. A is that quantity C1 plus 2C2 plus, I'm going to take n minus 1 times the maximum. If I take the maximum of this function on the whole line, of course the maximum is bounded. I have a minus here, so I can estimate from below. So maximum on the whole line of psi prime divided by r squared. So I call A this number. And then what we get from here is the following. So 0, bigger than or equal. Then you will see now, I'm going to write something that is already right. I'm going to write something and then explain it, okay? So I need to go a little bit faster, otherwise we will not get to the end of this thing. So I will explain. Squared minus phi squared capital F over t. And let me put here a phi, so I put phi squared, and then I have minus a f phi period. So let me explain. What have I done? I'm starting from here. I have this thing here. Okay? So this thing is controlled from below by this. So I keep going down with the inequality. If I put absolute value here and I estimate, so you see, gradient f is controlled by, is equal to minus f gradient phi over phi. So you replace this information in here. So you can express everything in terms of gradient f, length of gradient f, length of gradient phi. Here, I'm multiplying this inequality throughout by phi. I can do it without changing the sign of the inequality because phi is bigger than or equal than 0. So I get the phi squared here. Everything else is the same. I get a phi squared here. Remember, this is alpha. So remember that this guy is capital F over T, the quantity here. So I get capital F over T times phi squared. And here, I majorize this term from below with minus A, because I put the maximum here. Okay? So that's the explanation of inequality. Questions?
Excuse me, let us return to the definition of f of capital F.
Capital F is T times this.
As far as I remember, alpha did not participate.
No. Alpha is in the definition of capital F. It's very important. Remember, we're trying to prove this, and here there was alpha. So capital, I'll write it again. Capital F is T gradient F squared minus alpha Ft. This is capital F. Alpha is any number bigger than 1. So I can write this as capital F over T. I have multiplied this inequality by phi. I do not change the sign of the inequality because phi is bigger than or equal than 0. Here, I have this times this, but this minus this is bigger than or equal than minus A times F. So that's where this comes from. Any questions? I mean, the arithmetic is simple, but you know, there is going to be a lot of calculations, so one has to make sure that all the steps are clear. So at this point, remember that this thing here was less than or equal than 0, so that's how we get this. Okay, so we are at this point now. So we are at this point. Okay, so let me rewrite this thing equivalently in a I'm sorry, what time am I supposed to finish today?
2 and
2:05? Okay. I have one question about tomorrow. Tomorrow, I don't, is there 2 lectures tomorrow? Okay. So what time? That means 3 hours. That means bad for you. You will have to drink a lot of coffee or tea to be awakened. So I will try to make breaks. I will try to make breaks. So tomorrow, do you know what time we start?
The first lecture starts at 2 with 15 minutes.
2 with...
Quarter after 2.
Oh, a quarter after 2, I see. Okay, so we go until 3, then 5 minutes, then 45, and then what?
10 minutes.
Then 10 minutes in between, and then we start again. Oh, tomorrow is going to be a killer.
These times correspond to bells in our university.
I see, okay.
the same schedule is in our
In university, I see. So except that bells ring. And,
yeah.
And do bells ring also when you have to start again? After the 5 minutes?
Yes.
I see, so you cannot pretend that 5 minutes is 10.
Not here, but at the university building.
Okay. All right, so it's more or less like in Italy. In Italy it's the same. It's, the 2-hour lecture is you have 15 minutes, and so essentially you teach 1 hour and a half. Like here, it's 90 minutes. I mean, it's the same. So, okay. So now let me rearrange this inequality a little bit. So let me see, what do we have here? So we have this gradient phi. So once again, gradient phi is going to be equal to 1 over r psi prime rho over r gradient rho. Okay, so if oh yeah.
Inequality for
what?
gradient.
I'm sorry, what?
I mean, we have inequality that get for delta, for gradient.
Yes, but what I'm saying is, so this is the final inequality with, that we arrived at. So let me rearrange that inequality a little bit, because it's, so I'm going to write it like this, because it's going to be useful for us later to write it like this. So phi over t times f, phi f plus 2t over n times gradient f squared minus ft squared times phi squared minus 2 phi f gradient little f gradient phi. Okay, so I have simply rewritten this inequality here in a different way. I have rearranged terms in a different way. I have put together this term here with this term here, in here. Then the other term is still here, okay? And then this one is at the very end. All right, so now let me erase this. We won't need this stuff anymore. And let me get some space. Well, I have to erase this inequality here, which is the final inequality, otherwise I won't get you know, any space to work. Okay, so what I was saying is that now let's observe that the gradient of phi is less than or equal than 1 over r times psi prime. Okay, so that simply comes from here, and the fact that this thing in absolute value is equal to 1 or less than or equal to 1. And then this thing here, now I'm going to use this inequality again and take the square root in this inequality to estimate this guy. So I'm going to get less than or equal than the square root of C2 divided by r times psi prime rho over r to the 3/2. Sorry, 1/2. Okay? So I'm going to be using this information in here. So if using that information, we get that 0 is bigger than or equal than minus a plus phi over t times phi f plus 2t over n and gradient f squared minus ft squared phi squared minus 2 square root c2 over r, and then I get psi rho over r to the 3/2 times f times gradient lift f. Is it clear to everybody where the 3/2 comes from? Here I get psi to the 1/2 after I take the square root. I have psi to the 1/2, and I also have another psi coming from here, so I get psi to the 3/2. Okay? And of course I don't need to put the absolute value because psi is non-negative by choice, but anyhow, it's there. So at this point we multiply by t in this inequality, and then we get this. So we get 0 bigger than or equal. Let me see if I can write it directly here without rewriting. So I multiply by t in this inequality. So I get this, I get rid of this, I get t squared here, I get t here, and that's it. Okay? So at this point, I mean, again, I'm following the argument of Li and Yao. So they take, now they have to prove a numerical inequality. So they take y to be phi gradient f squared, and then z to be phi times ft. And notice that y minus alpha z is equal, y minus alpha z is equal to phi, which multiplies this. And remember that the gradient square of f minus alpha ft is capital F divided by t. So this is equal to phi divided by t times capital F. That special combination. Okay? Let's also notice that phi squared, so this is equal to phi times y, and this is less than or equal than y because phi is bigger than or equal than 0 and less than or equal than 1. I will use this little thing later. So anyhow, at this point, I'm going to go, so let me look at y to the 1/2 times y minus alpha z. This is equal to, I'll leave it to you to check this calculation. Is just replace, this is equal to this. So y is this guy, and y minus alpha z is equal to this. Replace everything, I guess you believe it, right? You take the square root of this, multiply it by this, and that's what you get. So in this notation, I can write now the inequality. This was my key inequality, which I ended up with. So I'm going to use this y and z notation to rewrite that inequality. And let's see what we obtain. I mean, it's clear, this seems all magic, but it's clear that, you know, they knew what they wanted to get, and so they worked very hard to, you know, it's not like they have pulled these things out of the hat. I mean, it's remarkable that they could get this part just with calculus. But, you know, that's what it is. So let's rewrite that thing. So we have 0 bigger than or equal than alpha t plus 1. Why have I removed this? Because phi is less than or equal to 1. I'm majorizing, I have a minus. So I majorize from below by replacing phi with 1.
Minus.
There is a minus. So now we have plus 2t squared. Let me see. Plus 2t squared. Let me first put this term here. Okay, so I have minus 2 square root of c2 t let me see, I multiply the equation by, I multiply the equation by t, so I should have a t squared here, not just t. Let me make sure. Oh, life is not easy. Where does the t squared come from right now? Well, let me keep this because I don't seem to have. I multiply this equation. Just bear with me for a second because it's important to know whether here, no, here there is just t. So let's keep the t there, and then we see what happens. Okay, and then we see what happens. So I have this thing times r, divided by r, and then I have psi to the 3/2. Wait. So this guy here is phi to the 3/2, because phi is psi rho over r. So let me see here. So this, if I compare this, and this, there is my t squared. Good. So I have t, and you see, here I have phi to the 3/2. F, gradient, little f. So that equals to t times this. So I'm going to write here t squared. Okay? I have t squared, and then I have y to the 1/2 y minus alpha z. Is that clear what I've done? I've used this identity here to write this term in terms of y and z. And I gain an extra t. Any objection?
Clear, clear, that's clear.
Is clear? Vladimir. Is okay? Good. Vladimir stops me all the time, so I have to be careful. So we get this, and now let's look at this term here. Let's look at this term here. So we write plus, so 2t squared over n, and then I have, let's see. So I can bring this guy inside. I have y minus z. So this is just y minus z squared. Is that clear? I put this inside. So I have right. Okay? So we get this inequality here. And now there is this magic thing that they pull out of the hat. I mean, they say, observe that y minus z squared. So in a way, this is the enemy, because they want y minus alpha z, because remember, y minus alpha z, I observed it before, is capital, it's here. Is capital F, and they want to estimate capital F. They want to control the supremum of capital F. So they try to force now, this term is the enemy, so they try to force y minus alpha z into this term. And so what they do is they write this like, so it's not like it's magic, there is a logic into it, of course. You have to know what you're doing. So let's check. So we have y over alpha here, minus y over alpha, they cancel. Then I have y, and then I have minus z. Okay? So everything is fine. Okay, so let's expand this. So we have y minus alpha z squared over this plus alpha minus 1 squared. Y squared over alpha squared, and then we have plus 2 alpha minus 1, and then we have alpha squared here, y minus alpha z. So this is this term. So what they do, they say, well, I'm going to replace this term with this object here. All right? Well, because they want y minus alpha z to appear. That's their friend. Y minus alpha z is their friend. Okay, that's what they want. Y minus alpha z is f over t multiplied by 5. Okay? So after replacing, what they obtain is the following. So this is a little bit of arithmetic. I will spare it because it's very boring. So 1 plus a t phi f, there's a minus here. And so here we get plus 2t squared over n y minus alpha z squared over alpha squared plus alpha minus 1 squared over alpha squared y squared plus, and now they write things in this way, plus 2 alpha minus 1 alpha squared y minus n square root c2 r y to the 1/2, which multiplies y minus alpha z. Okay, so I have to ask you to just check that things are like this. You know, when you multiply this times this, you get this term here. When you multiply this times this, you get this term here. So everything is fine. So this inequality, after you observe that y minus z squared can be written like this, you replace this, then you can rearrange the inequality in this way. Remember, once again, you want y minus alpha z to show up. There is a logic. I mean, it's not like, I mean, for them, this was the enemy. They don't want this guy. So they want this guy. And this is why they force the situation in this way. Okay, so now we get to this inequality here. And now there is another clever trick. You know, these are just simple numerical observations. So I can erase this now. Now they complete the square. So they have a product, they complete the square. And so these are very elementary but clever considerations. So they say 2 alpha minus 1 over alpha squared times y minus n square root c2 over r y to the 1/2. So, I mean, this is the square of this guy here, so they try to complete the square. So you can write this as the square root of 2 alpha minus 1 divided by alpha y to the 1/2 minus n alpha square root of c2 2 square root 2 alpha minus 1 r squared. Okay, fine. This is what it is, and then you have to subtract what you have introduced. So n squared alpha squared c2 divided by 8 alpha minus 1 times r. And then they say, okay, I can write this object in this way minus this. Now, this is the enemy for them, because I've introduced this guy here, I don't want it, but this is a square. So I can throw this away and just okay? I'm sorry, but here there is a square. And here there is a square. So is it clear? We simply throw away the square that we have obtained completing the square. And we go back to this inequality here, and we say, well, let's see. This thing here is what I can estimate it from below by this. Aha, but wait a moment. I'm multiplying by something, and that something could be negative, so I change the sign to my inequality. I'm dead. No, I'm not dead, because y minus alpha z is phi times capital F divided by t, and capital F is positive at the maximum point. Everything here takes place at the maximum point. So this term is a positive term by my initial assumption that f at x0 t0 is positive. And therefore, if I multiply this inequality by y minus alpha z, I preserve the inequality. That means that this now can be continued, replacing this term from below by minus this multiplied by y minus alpha z, which is what I'm going to do now. So So the conclusion of all of this is, and now you'll see that we are almost finished. We're really almost finished. So please, bear with me. I know that, ooh, I'm already over time.
There is alpha squared, yes?
Where?
Alpha squared.
Where is
The
it?
last one. No, on this side. Alpha squared.
Alpha squared. Thank you. In the end, you know, alpha is any number bigger than 1. So alpha squared, unfortunately, even if I make a mistake, is not going to impact the final inequality. But it's there. Thank you. So,
Let's finish.
can I finish this few minutes? It really takes
Okay.
5 minutes at this point. I apologize for going over time.
Yes.
But you know, tomorrow continuing it from here is going to be a disaster because we have to remember all these things.
It will take 1 more hour.
So as I said, let me just write what we get at this point. Okay, so in the end, we get 0 bigger than or equal than phi times f, which multiplies 2 over n alpha squared phi f minus 1 plus 8t plus n alpha squared c2 t divided by 4 alpha minus 1 r squared. So let me close the bracket here and let me... Alright, so where does this come from? This comes from replacing this observation in here, and then rearranging terms. And remembering that y minus alpha z is equal to phi f over t. So at this point we are finished. So this is true, this inequality is true at x0, t0. And x0, t0 it was a point in B2R Cartesian 0 capital T. Okay? So since that was the maximum point, that means now that I can get information. What I get is the following, that phi f at a point x capital T for any, say, x in BR. So this is less than or equal than n alpha squared over 2 plus n alpha squared over 2 times a plus n alpha squared c2 divided by 4 alpha minus 1 r squared times t. Okay? Remember, here I have 0. I have this difference is less than or equal than 0. So it means that this is less than or equal than this, and therefore this is less than or equal than this, divided by what I get here. Okay? So at this point, I guess that we are finished, because recall that phi is identical equal to 1 in BR. So at any point in BR, this phi is gone, and what I get is this. So at this point, capital T was any number in which you have, you fix a number and you look for the supremum x0, t0 in B2R Cartesian 0 capital T. So we have estimated that supremum, and therefore we have estimated f here. T is any number, so now divide by, so you can get rid of this. Divide by t here, you divide by t here, and you kill this thing. And that's the estimate in the theorem of Lee and Yao. Capital T was an arbitrarily fixed number. So call capital T little t. And we are finished. So you see, the magic number n over 2t is here. Alpha squared goes to 1 as alpha goes to 1. And we get the estimate of in the theorem of Lee and Yao.
And any capital is some constant, yes, depending on C1 and C2.
These are just absolute constants, you know, C1, C2, they are absolute constants. So in the end, you get a number which depends only on the dimension of the ambient space. You see, there is no other dependence.
How about the capital A?
Yes.
Does it participate in the...
No, because there is a mistake here. There is a mistake. Let me see. No, there is no mistake. Remember the definition of capital A. Capital A was a bunch of things divided by r squared. So this is still good. When you let r go to infinity, this guy is going to go to 0.
Yes, and when r goes to infinity, don't you need some restriction on topology if the ball some injectivity radius?
No, because no, you don't need. You have a complete manifold. Okay, so completeness means that there is that completeness is equivalent to the property that there is an exhaustion of your manifold with balls of arbitrary radius.
So you, for any manifold, even with non-negative reaching,
Completeness, yes.
You can,
Yes,
you can
absolutely.
go to infinity.
Absolutely. This has nothing to do with Ricci, with curvature. If you have a Riemannian manifold, completeness is equivalent to the existence of an exhaustion of the manifold with geodesic balls.
Yes, but I mean, when the r goes to infinity, it would intersect itself, the ball. No,
That's not.
It doesn't matter.
That's not the problem.
Okay.
I have the assumption of non-compactness. So, you know, you can go down, up, you can go up to infinity and swallow the whole manifold. So we're done with this. I apologize for going over time, but it was